Log on, tune in, find out. Another good idea from Cambridge.
Professor Ramanan from Chennai that he will talk on representation of the fundamental group and geometric loci of functions.
So, thank you. This is my first ever lecture in Cambridge. Better late than never has never been said more appropriately. So, I thank the organizers, Peter, Leticia, Oscar, and whoever else for inviting me here, and the British High Commission to have provided me with a visa, albeit late. Okay, so the lecture will be very elementary. I don't think you will protest, particularly soon after lunch, when everybody is somewhat sleepy. So, let me start. All the assumptions I make are not absolutely necessary, but I will assume for simplicity many things. So, C will be the algebraic curve, projective, smooth, complex algebraic curve. Pi the fundamental group, occasionally pi can also be a map, but let me try to avoid it. So, suppose everybody knows that you have a map from pi to S1. Then you can take the universal covering and take the associated bundle, that will be a line bundle. So, you get a line bundle, and this gives a bijection between characters on pi, unitary characters, and line bundles of degree 0. So, this is where I start, and soon one asks how about representations of pi 1 in other groups. For example, I will take S1 is contained in SU2 as diagonal matrices, and you can take the group generated by S1 and perhaps this. I guess that's right, but yeah. Okay, so take the group generated by this, call it N, generated by S1 and this, and suppose you have a representation of pi into N. Now, you have an exact sequence 0 to S1, this is index 2 there, because when you square it becomes -1 and which is in S1. I I don't know whether I should write 1, yeah, it's not a million, isn't something wrong? Yeah. So, you have a map from, I am assuming, since we understand pi to S1, let us say assume this does not factor through in S1, you have a homomorphism from pi to n. By composition, you get a surjection from pi to S2, and you have a surjective quotient of the fundamental group, therefore, you get a covering. So, whenever you have a homomorphism here, you get a covering C to C tilde, a two-fold covering, étale, it's a covering space, étale to sheeted. So, we might as well write pi z mod 2 here, and take the kernel. This is a fundamental group of C tilde. You have a map like this, you have a diagram. The advantage is, of course, now we have pi tilde to S1, which we understand already. So, you get a line bundle. Yeah, before I go to line bundle, let us analyze this representation itself. So, you can ask conversely, if you have a map from pi tilde to S1, when can you extend it to a map pi to n, such that the diagram is commutative? So, there are necessary conditions, let us write it down. Yeah. First of all, you take what is pi tilde? I said it's a fundamental group of C tilde.
What is C tilde?
C tilde is all two sheeted covering given by the map pi to Z mod 2.
But no, for the converse, I must. You asked a question, pi tilde to n, S1 is already been a mapping.
Yeah, I am suppose given a map pi to Z mod 2. Yes,
What's the question now? The question is, given a mapping of pi tilde to S1, can I list two to something you asked? No.
yeah. If you have a map pi to n, you will get a map from pi to Z mod 2. So, fix that. Then ask whether you can extend it in such a way that the composite is the given covering. Is it clear? Okay. So, now you take a non-trivial element, that is non-trivial meaning which is in pi tilde, but not in pi. So, there is a character on pi tilde. On the set of characters, I do not know, it is very clumsy, maybe this is a set of characters, unitary characters on pi tilde. On this Z mod 2 acts, because Z mod 2 acts, pi tilde is the normal subgroup in pi, therefore, Z mod 2 acts up to inner automorphism, therefore, on characters it actually acts. So, this is a pi tilde hat, this is a characters on pi tilde. So, Z mod 2 acts. On the other hand, Z mod 2 acts on S1, and of course, it has to be equivariant. If the diagram is to commute, then it has to be equivariant. So, therefore, this character must be equivariant for this action. So, actually it goes down to, so which effectively means yeah, okay. So, that is condition number 1, that if you take the character pi tilde to S1 twisted by Z mod 2 by inner automorphism. So, you get another character that should be equal to this Z mod 2 acting on S1. Now, this Z mod 2 acts on S1, I wrote down the matrix. So, it is not very difficult to see how it commutes, how it maps. It takes T to T inverse in T. Unfortunately, this does not split this exact sequence 0 S1 enter Z mod 2 does not split. In fact, it is a unique non-trivial extension of Z mod 2 for the action Z mod 2 on S1, which takes t to t minus 1, non-trivial element acting as t to t minus 1. Okay, so this is condition number 1, and I can give you another condition. Take an element x, take some set theoretic splitting of pi to Z mod 2, say take x in pi, but not in pi tilde. So, it maps on a non-trivial element. I need to take the square. So, it belongs to pi tilde. X squared belongs to pi tilde. And you can take, let us call this chi. So, chi of x squared is independent of x, because instead of x, if you replace it by Tx, then you will square this Tx, which is the same as T x T x inverse x square, and apply chi to this, so chi of Tx square equal to chi t. It is also in t, and we saw this is the action on t by Z mod 2, and we are assuming that it is equivariant. Therefore, this will become t minus 1, it cancels chi x square. Therefore, whatever element you take in the complement, the square chi x square is independent of x, and this is an element chi x squared square is equal to chi x squared is chi x squared minus 1, because x commutes with x squared. Therefore, the Z mod 2 action fixes this. Therefore, if you apply this, it should become minus 1. So, this is equal to this minus 1. So, chi x squared is an element of order 2, and so let us say chi x squared is minus 1. So, these are the two conditions I am going to assume on chi. So, as soon as if it has to extend, it has to satisfy these two conditions, and it is a simple matter to check that this is necessary and sufficient.
So, from the line bundle point of view, the Galois involution should take it to dual, right?
Yeah, I am going to say that. I started with the remark that unitary characters give line bundles. So, in particular, this map pi tilde to S1 applied to C tilde will give you a line bundle on C tilde. So, this is a condition on the line bundle on C tilde, because there is a bijection. Therefore, we have a line bundle on C tilde, and then we have put some conditions on the line bundle. So, everything can be translated in terms of the line bundle, and so one of them is that if the Galois involution IL should be equal to L inverse, because the character rate acts as chi t to chi t inverse, and therefore, L will go to L inverse. So, Galois involution should take L to L inverse, and the second one can be translated to say that norm of L, whenever you have a line bundle, you can take norm on C, represented by a divisor, take the image and take the line bundle. So, that is the norm. So, norm of L is equal to alpha, where alpha is a line bundle on C given by the character pi to Z mod 2, Z mod 2 being represented by plus or minus 1 in S1. So, we have a unitary character on pi. So, which will give you an element of order 2 in the Jacobian, call it alpha, and that gives this covering actually. So, so in some sense it is a prim variety on C tilde. And what is more, you can check the following that so L and the Galois twist will give rise to same extension. The extension is, you can see how unique it is. I do not want to spend too much time on this. And so, the geometric analog of this or vector bundle analog of this will be that you take the prim associated to alpha, as Narasimhan said, alpha has been given, that is the action, the map from pi to z mod 2 is given, and then you ask whether it can be extended. It can be extended if and only if. So, you take an element in prim alpha and then you get, so this is one, and L inverse will going to, the Galois twist of this will also give the same thing, and my assumption is Galois twist is L inverse. Okay, so L and L inverse give the same element in home. Okay, so the corresponding bundle below is an n bundle. So, the assumption is that norm of L is alpha, that is why I call it prim alpha, and of course, I am assuming I star L equals L inverse. So, take a line bundle upstairs such that the Galois twist is L inverse first of all, and secondly then the norm should be equal to alpha. From this you can check actually the norm is either trivial or alpha, and I am assuming it is alpha. Then you take the line bundle L, and these up to Galois twist of L inverse gives the same thing. So, if you take the quotient by L to L inverse of prim alpha, it is in bijection with, like as I said, some objects on C.
It is same in element in home pi n or home pi n mod n. You say give same element in home pi n. L and L inverse.
Yeah, equivalence classes.
Yeah,
Equivalence class. Okay, so this is bijection with n bundles, but n bundles can also be embedded in SU2, and then you can say vector bundles. So, you get a vector bundle of rank 2, and the fact that it is in n can be restated as saying that alpha tends to E. So, E is a vector bundle of rank 2, and alpha tends to E is isomorphic. This comes from the fact that if you have a map of pi to n and you take minus, I mean pi twisted by the map from z mod 2 plus or minus 1, that means you take this map and twist it by that, and then that is equivalent to this. In fact, there will be equivalent by conjugation by that matrix, you can check that, and therefore, alpha tends to E is isomorphic. Okay, so, this is a representation theoretic picture, and that is a vector bundle picture. In fact, one can actually show that this E is actually pi star of L, the direct image of L. Okay.
Trivial determinant.
G?
Trivial determinant.
E will have trivial determinant, because norm L is alpha. Norm of pi star of L, the determinant of pi star of L is norm tensor alpha, and then you can check that. Therefore, but I must warn you this, although I read prim, it is not connected, it has two connected components. and the involution leaves each connected component invariant, therefore, we will have two connected components, that is the map. So, next we can look at, of course, we have T as S1, we have also representations of, by the way, the very condition that alpha tends to E is isomorph to E will force E to be semi-stable. Indeed, polystable. In fact, so you can generalize this. Instead of taking a map into S1, you can take a map into a compact Lie group, connected Lie group, and then that will be, as one knows that this is equivalence class of maps into of pi 1 into a compact group is a non-one correspondence with polystable bundles, isomorphism classes of polystable bundles, the GCA structure group, the complex classification. As you know, this is Narasimhan-Seshadri theorem in the case of GLN, and it was later generalized in this context, in the context which I said, by A. Ramanan. Okay. So, it is a natural generalization to think of. Now, you can take a compact connected Lie group, T is the maximal torus, and you can look at representation of pi 1 into T into NT, the normalizer of T in G, and you have the exact sequence 1 T NT, the while group of G. You have the map pi 1 to this. Well, the image may not be W, but I will write W, you can replace it by a subgroup if you want. Instead of, that is what I said. So, I will assume it is W, but it is not necessary. You can take, for example, it is very interesting to take even in the JLN case when the image is a cyclic group instead of the whole symmetry group. So, it is it's interesting, but for notational simplicity I can replace it by W prime, a subgroup of W, and then replace it. So, you have this, and then you take the kernel, call it pi tilde. So, you get a covering C tilde to C. Now, you can ask the same question. Given a map of pi into W, that means given a covering here, and a T homomorphism of pi tilde into T, which is essentially a lot of tori, right, a lot of characters on pi tilde. In fact, this can be thought of characters on T to characters on pi hat. Right, you can compose it, then you will get. So, dually you can give that, that will give you this map. So, you can ask when it can be extended. The answer is very similar. So, you know W acts on pi tilde up to inner automorphisms, because it is a normal subgroup, and W acts on T, that is raison d'etre, and and this morphism must be equivalent for that. This homomorphism must be equivalent. That is first condition. That is the condition 1 which I wrote. In condition 2, there I gave a hands-on definition. It is better to do the following. You take this extension. This extension will give you an element of H1 W, this is non-abelian, but if you are given a character, therefore, you can take this extension and then push it forward. Whenever you have an extension like this, and then you have a homomorphism of pi tilde into another group, you can push forward and get an extension of W by that group. So, this gives you, as soon as you give me a character here, I will give an extension of W to T, and that should be the same as this. That is the second condition. Otherwise, I cannot extend. Okay.
Taking the associated constructions. Taking the associated construction, right? Push up.
I don't know. Perhaps.
So some co-boundary mapping in common.
Pardon?
This is some co-boundary mapping, some appropriate homology to.
Maybe.
Push forward or extend?
Yes, I must confess here that I don't look into literature too much. I just do things myself. So, if I don't give proper references, please excuse me. Okay. If I do write it up at that time, I will check whether it is known or it is not known or so. So, the condition is that this extension push forward to T must be this extension, and this is almost trivial. If, for example, for SL2 it is not trivial, I told you, but for SL3 it is trivial. All odd SLs it is trivial, this extension is trivial, and I think it is always an element of order 2. So, up to squaring that becomes trivial. So, okay. That has to do with while group, whether while group sits inside NT or not, it does up to Z-mod 2. Okay. This is not a split extension always, sometimes it is, sometimes it isn't. So, that gives you a condition. Fortunately, it gives a condition in SL2, otherwise we might think that it is always trivial. So, okay. So those are two conditions, and then if those are satisfied, of course, it extends from pi to NT. So, these are the two conditions. Now, we have to go to vector bundles or G bundles. So, since you have a map from pi tilde to T, you get a T bundle here, L is a T bundle. Then what is the first condition? It is obvious. The deck transformation group acts on line bundles. So, W star of L makes sense. On the other hand, L is a T bundle, W acts on T, and therefore, by associated bundle you will get a WL. So, you should be equal to that. Be careful, W is non-abelian. So, make both left actions if you have appropriate notation, and then say that must be equivariant. Okay. Is it clear? So, another way of saying that is that you have L over C tilde, have W over C tilde, that is L. There must be an isomorphism which lifts this. Shall I write W tilde? No, that W tilde is confusing. So, okay. No, that is also confusing. Omega. Okay. Such that omega of psi S, S is in the group, psi is an element L here, S is in W, this is equal to omega psi WS.
Left and right matters in this case?
Yeah, that is what I say. I am a bit lazy, I am saying that make both of them left and then say it is equivariant. Obviously, left multiplication cannot commute with right multiplication. So otherwise you put an S inverse, that is all. Okay. So, permit me that loose talk there. Okay, so such a thing. So, that is my assumption on the T bundle upstairs. That is the first condition. Now, what is the second condition? The second condition is as follows. Now, I will make a new group, which I will make bold to say Heisenberg group, which is C tilde acts here. This lifts I know, but the lift should also be given. So, you take pairs W, I am very sorry that I choose notation like this, W and omega satisfying this, okay, and you can make that a group, because while I can lift one W, W1, I lift another W2. For W1, W2, my lift may not coincide, right. I may not be able to consistently lift like this. Okay. So, I can make a set of all lifts, I take W and omega, and I can make this into a group, and you can forget omega. So, you will get a map into W, because I am assuming for every W there exists omega. So, this is surjective. And what is the kernel? The kernel is T. Because if W is 1, W psi is W psi T s, then you can check that it is. You can define W omega up to T, up to multiplication by an element of T.
Automorphism of T bundle is T, that's all.
T, that is the point. So, you have this extension. So, this gives you an element of H 2 W T, if you do not mind that. Okay, so, the condition is that this should be this extension. So, that is the second condition. Is that clear? Then and only then you can extend it to NT. So, this is from the, I am taking too much time. Does not matter, at some point I have only said some representations. So, I will stop at that point. Okay, so, we have this extension should be that extension, that is the point. Then you can extend. Okay, so, yeah, I have already done this there. So, I have done it in the vector bundle sense, in the bundle sense. I said it first in the representation sense. Is it clear?
So, okay. As a G bundle, you want to give a reduction generator to NT, is it?
NT. So, I said there NT satisfies this. So, I have to say what this satisfies. And what this satisfies is the following. I am saying on C, so in other words, you get a G bundle, but I want an NT bundle. So, a G bundle can be restricted to NT bundle if there is a section, as you said, of the associated bundle with the principal bundle modulo NT. Okay. That is a bundle with G mod NT as fiber, but G mod NT can be identified with the set of all Cartan subalgebras in the complexification, because if we take a set of any two Cartan subalgebras can be taken one to the other by an adjoint transformation, and if the Cartan subalgebra is normalized, so it will be in NT. So, G mod NT can be thought of as a Cartan. So, in other words, I have a Cartan bundle here. So, claim or theorem, if you like, that you take the adjoint bundle. So, I am given a T bundle, right? Yeah. So, upstairs, that is equivalent, this gives an NT bundle below under these two conditions. An NT bundle gives you a G bundle. So, I am trying to describe now which G bundles occur this way. There I said if E satisfies alpha tends to E is isomer of T. So, I want to say what is the corresponding thing here, and it is the following. So, take T and then take NT and take the corresponding G bundle. So, you get a E G bundle. So, if L satisfies 1 and 2, it gives rise to a vector G bundle with a reduction to NT which satisfies. So, I call it E. So, I am going to describe this dot dot dot. additional condition, the reduction of E to NT.
So L is a G bundle on C tilde or on C?
A C tilde,
On C tilde.
C tilde.
What are the conditions 1 and 2?
L is not a line bundle, a T bundle, yeah,
It's G bundle.
yeah,
But on the covering.
on the covering.
What are the conditions 1 and 2?
That if you twist L by a deck transformation group element,
Is this
the
linearization?
W star L should be the same as the associated bundle for the action of W on T. That means it should lift like this. And the second condition is the corresponding extension should be the extension in the while group construction. If these two conditions are satisfied, then you can extend it. Therefore, you get a NT bundle below, and which is the same as a G bundle with a reduction. So, I want to describe what is this reduction, give it in a more tangible fashion, or more familiar for us fashion, which is you take a G bundle,
You are going to describe the G bundle or the T bundle?
NT bundle.
NT bundle. That
NT bundle below I am going to describe as a G bundle with a reduction to NT. The reduction to NT is to give a Cartan subalgebra and the Lie algebra. So, we take the Lie algebra bundle, which we call it ADE. At every point you should give a Cartan subalgebra. What is that Cartan subalgebra? How does it come in this case? You have C tilde to C is a W principal bundle, and W acts on T and therefore on the Cartan subalgebra. So, W acts on the Cartan subalgebra. Therefore, you have an associated bundle G, and that is contained in E. Okay. So, let us say it is a Cartan bundle contained in Go back to SL2 if you are a little confused. This is a two-sheeted covering, the associated bundle will be alpha, and I am saying alpha is contained in IDE, which is the same as saying alpha tensor E is isomorphic T. So, it is a sort of Higgs. In the morning we have generalized the line bundle to vector bundle, so we do not bother. So, you get some kind of Higgs in this case also.
Is this considered the same? See, W acts on NT. So, given a W bundle and NT bundle, you can get another NT bundle by using this action, and you are already given a W bundle to start with. So, this action of this W bundle should take this NT bundle to itself. Is that the condition?
No, but I am given a G bundle. I am asking what are the G bundles which arise this way. Okay, and then you can check that this is always polystable. If you give this condition, then you can go converse. If you are given an NT bundle, we have checked after all, more or less we have checked everything. Okay. All right.
Now, suppose you ask the question whether the NT bundle, what is the characterization of the NT bundle itself? Suppose the NT bundle you have. Isn't it the same thing as saying W bundle takes the NT bundle to itself?
If you will defer the question to the end,
Okay.
because I want to get somewhere. Then it is a question hour, so it does not matter. Letitia will not object.
I'm sorry, I want to stop just because I don't understand. It's nothing.
Sure.
See, so in other words, I mean, you want to give a Cartan subalgebra at every point.
At every point
Line.
of the adjoint point.
Adjoint.
You have a Lie algebra there, you want.
What's the construction you said now?
What is the construction? I did not say the construction. I said there is such a Cartan subbundle,
Definition.
namely
Given by the reduction.
given by the
Associated
no, associated. This is a W bundle. W acts on the Cartan subalgebra. Therefore, you have a Cartan bundle,
That's all.
and that is contained in ADE. You can check easily. And conversely, if you are given this, you are given after all you are given a reduction to NT, you get an NT bundle.
case when G is SLN, is this just going to be pi star? Oh, sorry, not pi, whatever, the direct image.
I have not figured it out. I'm thinking about it, but I haven't figured out the correct restriction of scalars or whatever. It seems to be some group scheme bundle and so on. I want to make it simpler. So, okay. All right. So let us leave this at that. Then let us go to something familiar territory. Suppose you have pi 1 into G. I will still use G, but this time G is a complex semi-simple group. Then we get, as we all know, I think everybody in this all knows that you get in this case a Higgs pair, which I originally called in my paper with Indranil a Hitchin pair, which he says now it's okay. So whatever. So you get so this way you get a bundle, G bundle, and a section of K tensor. Not K is not arbitrary now. K is the canonical bundle, canonical line bundle. Then K at B. And this pair is polystable. So you get, if you take a reductive representation of pi 1 to G, in the case of JLN, that means it's a completely reducible representation. Then you get a polystable bundle. And that gives an equivalence between isomorphism class of polystable bundles and equivalence class of representations into GC. Now, so you can do this even for T. You can take, instead of T, you can take C star, you can take GM, and then you can take a map. And then you get not merely a line bundle, but you also get a form, because that's adjoint is trivial. So you get a section of K, so you get a form. If you take NT, so what do you get? You get, in addition, a section of a form, a twisted form, K tensor alpha. So you get this NT bundle, and then there is a K tensor alpha, a section of that. K tensor alpha below. So the sections upstairs of its K will decompose into sections which are invariant into the Galois, that means forms from below, plus sections for minus 1 eigenspace for the Galois convolution, which is section of K tensor alpha below. So, did I make it clear or succeeded in confusing you? You take the complex case, take GM and then take NGM in SL2C. Now, we have representation into this, you get the old stuff plus some extra clothing, and that is given by a section of K tensor alpha. Upstairs, you have a map into GM, therefore, you will get a line bundle plus a section of K, but this has to satisfy I star alpha equals L minus 1 in the L star, in the sense he gave in the morning, namely, if you take the dual, it must be isomorphic to dual Higgs should be isomorphic to this. So, which can be interpreted as saying that I am given a section of K tensor alpha below. It is a minus 1 eigenspace for I upstairs. Okay, so I have finished the T case, I have done the NT case, I have done the GM case, I have done the NGM case. So, now I am going to complex case that we know very well, complex semi-simple case. So, let me go into other cases when we have seen, if you take a complex semi-simple group, there are various real forms that G admits. Okay. So, you can take for example, the compact form. So, all forms, all real forms are given by conjugation, complex conjugation, anti-automorphism. Shall I write sigma? Anti-automorphism, anti-involution. In other words, sigma squared is 1 and sigma of in the Lie algebra, sigma of lambda x is equal to lambda conjugate sigma x and sigma squared is 1. So, you take the fixed points, you will get the real substratum of the real algebra, real points of the real structure on that. So, you take anti-involution and Elie Cartan already showed that any other real structure is conjugate, any other involution is conjugate, in fact under an inner automorphism to this sigma, to something which commutes with this sigma. I repeat that if you have a conjugation, then you have an automorphism and then you take A sigma A inverse, essentially it gives the same real structure. Because what we will say is a real structure, it is a real algebra such that with an isomorphism of G tensor C with the given Lie algebra. So, if you take an automorphism, then it will take sigma to A sigma A inverse, this to be considered equivalent. So, if you are interested in knowing all real forms, you might as well as you take those which commute, because he proved that given any other real involution, you fix the compact involution, fix it forever, and then you say any other involution is conjugate to another anti-involution which commutes with sigma, which is the same as saying that there is a involution, complex involution, and then A sigma. A commutes with sigma. So, every other involution is conjugate to one of these type where A is an element of order 2. So, using this one can show the following. Take involutions modulo, say two involutions are equivalent, say A and B are equivalent. If there exists, there are two possibilities here. I will say there is an automorphism. So, shall I write this and this prime? Okay. Respectively. If there exists C in OT such that C is inverse B respectively in int inner automorphism such that this. There are two possibilities, and one can show by following Cartan that whether you take involutions modulo this equivalence or you take conjugations anti-involutions modulo this equivalence, there is a complete bijection. The bijection is given exactly like this. So, if you are given a conjugation, then it can be altered by some other conjugation tau. Sigma is fixed. If you are given some other conjugation tau, it can be conjugated to an element of the form A sigma, associate A to it. That is not unique, but up to this equivalence, that will give you, that is enough to give you a bijection of these equivalence classes. Okay. It is a bit subtle, so I give you some time to observe this. So, now a strange fact. Certainly, for an algebraic geometer, it is certainly strange that this involution, compact involution, think of it in the complexification. So, you get a this is a complex group, then you take a G bundle twisted by this involution sigma, which is anti involution, the compact involution. So, G bundle will give you a Higgs pair, and by associated construction you will get another Higgs pair. So, you get a map, you get an involution of the moduli space of G bundles. And the strange fact is that the induced map is E phi going to E minus phi. It is strange, I repeat again and again, because what we have is a complex conjugation, and here what you get is actually a complex analytic map. Okay. As you know, this E phi is constructed by, if you are given a representation to GC, you are constructing E phi by means it is not the associated bundle. You make some, you solve some differential equation, change the complex structure, and you get 2 feet, one of them is E and the other is phi. So, so maybe
Fourier form do we take here?
Compact form. Compact form. And therefore, for every real form, the induced map is analytic, because every other, if every other thing is A sigma, A is a complex analytic. It is not perverse. If you have G to G something complex analytic, you will get certainly a complex analytic map here.
On the Higgs
Therefore, all of them on the Higgs model space, every real form will give you an involution. Okay, now, in a way, it should not surprise, because if it is a compact, if the representation goes into a compact group, then it is just a vector bundle or a G bundle, the phi part is 0. Okay. And the fixed group for the complex involution is a compact group. Therefore, if you want to see here what is the fixed points, you will get E 0, and which is correct, because that is the compact form. Is the point clear? That if you take a compact conjugation, the fixed point is a compact group. So, if you have a representation into the GC, into G, the fixed points will be presumably representations into the maximal compact, and therefore, it will be E 0. Everything is fine. In fact, one can show this if E were stable, because if this is isomorphic to this, there must be an automorphism of E which takes phi to minus phi. The only automorphisms of E is lambda, multiplication by lambda. It cannot take phi to minus phi unless phi is 0. However, there are other fixed points. Why? It is because although E phi may be stable, this is the only case I am going to discuss here. I am not going to bother about it being non-stable but polystable. So, if you take E phi, at least this works when E is, by the way, if E can be stable but not simple in the general case. So, I am assuming it is simple for conclusion that E phi should be 0. Okay, so now okay, so what do I want to say? Yeah, there can be other fixed points. For example, you can take This is because this is not actual equivalence. You see, the point is that if this is equal, phi equals minus phi, of course phi is 0, but it can be equivalent to this. So, given the representation theoretic sense, if you are in SL to R, in the Lie algebra of SL to R, which is phi is more or less morally an element of the Lie algebra. So, if you take a semi-simple element, the eigenvalues are lambda minus lambda, trace is 0. Therefore, minus will be eigenvalues minus lambda and lambda, which is conjugate to this. So, there may be an equivalence which takes this to this, and which does happen. And in fact, one can show, for example, SL2, you can take L direct sum L inverse, and then you want to map from this to K to L plus K to L inverse. So, you can write it as a matrix. For example, if you take 0 0 and beta gamma, beta not equal to 0, with suitable degrees. For example, you can take degree minus g minus 1 and so on. So, you can check that if you take something like this, as I said, if L squared is k, there will be a map here, and so you can write it as 1 and so on. Then you can check this is actually fixed under this. Am I making sense? Like if you take bundles of this sort, for example, L square equal to k, that will give you a map from L to k to L minus, which I have written as 1, L square equal to k, and this will be a section of k to L square. So, take this as the Higgs thing, then you can check that this is equivalent to minus 1. Okay. And this we call the Hitching component. Why? It is because L can vary. So, this is the Hitching component, because these are actually amazingly SL to R representations of the fundamental group. These correspond to SL to R representations of the fundamental group. And notice SL to R is not simply connected, or its fundamental group is Z, because it's the compact part of it is SO2, which is S1, and pi 1 is Z. And therefore, even topologically, every bundle may not be trivial. So, it can have many degrees depending upon what degree you take for L. I said degree L is it's a square root of k, so degree will be g minus 1. So, this is not, the bundle is not stable, but the pair will be stable if you take like this. Okay. So, and these correspond to one of the components of the representation into SL to R, which is another real form. So, the question arises, I took E phi to E minus V, hoping that I will get only the compact form, but in addition I also got the SL to R form. So, it is crying for an understanding of this. So, you get the split form and the compact form representations into this, both of these as fixed points for this involution. Now, if I took SL3R for example, you get the compact form, of course, if you take E phi to E minus V, but you do not get the split form. Okay.
SL3C.
SL3. Sorry. So, one has to understand why, because you can make immediately a conjecture all the real forms will be fixed. The answer is no. So, so I will conclude by saying what is the answer. The answer is the following. You remember this, you have to take all real forms are given by involutions modulo this or this, two equivalences. Now, take this equivalence. So, you have the exact sequence 1 int out out. Okay. Now, if you take this equivalence, this is the one relevant for taking all compact forms, but take this. Okay. So, these are involutions, one compact form is fixed. you take involutions, complex analytic involutions, and you say two things are equivalent if they go one to the other by conjugation by an inner automorphism. That is this equivalence, I remind you. Then if you take two such things, they will have the same image here, because I am only altering things by inner automorphisms here. They will not be the same if I take the complex conjugation, because if you take conjugation by outer automorphism, it will give you conjugation in outer automorphisms. If two things are conjugate here by an element of out, their images will be conjugate by an element of out. So, we will get only a conjugacy class. But if I say two things are equivalent, if they go by inner automorphism by an element of int, then they will have the same image, because int goes to trivial here. Okay. So, under that equivalence, there is a map from that equivalence class into out 2 elements of order 2 in the outer automorphisms. So, you ask,
Is it in, out, and out of what?
pardon?
Just of a general group or by one? Or
Group.
which or G? What?
G.
This is a discussion about these things for G.
It's a G, yes, a G.
Or by one.
I got a little rattled because I want to assume G is simply connected. Okay. Okay. These are inner automorphisms, all automorphisms, outer automorphisms. I am saying two elements of order 2 here are equivalent if they go one to the other by a conjugation, not by an element of out, but by an int. Then they will have the same image in out. So, you fix an element of out 2. Why? Because automorphisms act on the moduli space. Okay. But that is not what we want. We want by the conjugation A sigma. That therefore, if you take an automorphism, so E phi, so I am studying E phi going to A E minus transpose A phi. So, I can say transpose A phi. Is it clear? So, this is how, if you like, transpose add A phi. I am taking automorphism A, it will also operate on the Lie algebra. The natural action will be minus, so I should write minus add A G. I was thinking of the complex case, minus add A G. Why? Because this automorphism will act on the moduli space by taking E phi to A E add A phi. Then I have to put the compact conjugation, then that will make it a minus. So, I am trying to take this involution of the moduli space, then try to find what are the fixed points. Okay. If you do not like it too much, you can forget about A. You can take E phi going to E minus phi. That is a compact thing. So, what are the other things that are available in the which are fixed? These are precisely those, take those automorphisms of order 2 which map on that particular outer automorphism and put this equivalence. And take those forms, those real forms, only those will occur as fixed points of this involution. That is the answer. I think I have exceeded my time. So, thank you very much.
Are there any questions?
So, your result is, if I understand, statement. You take some simply connected, maybe whatever. Okay?
Yeah, that's all in the result.
Okay. Then you will give me a special class of real forms for me. Just depending
Yes,
on
yes.
this, okay?
Yes, which I will call inner type if you like.
Particular contain the compact form?
Hmm?
No. It will always, this set will contain the compact form or not?
No,
No, not
it
necessarily.
may or may not.
Okay, you will give me a set of forms.
Hmm.
So that if I take any sort
No,
of.
if you fix an element of outer automorphism of 2, then I will give you a set.
Yeah, if you fix an element of and then you say, given any curve or whatever and so on, and the fixed point set will be of this.
Of those real forms,
Only
representations into those real forms, which each, of course, may have many components.
Okay, I understand.
In the case, the Hitchin case, in the SL2R case, as Bika, it's not here. So, sure that there are so many components, 2G minus 2 components. A priori, there can be infinitely many components because S1 is the fundamental group, pi 1 of S1 is the fundamental group, therefore, topologically there are many things, but there is no polystable stuff with that Euler class.
Even after reducing it to a real group, that modelized space has so many components.
Can have a priori infinitely many components, if that is exactly happens when the Hermitian symmetry case, because then the compact real, the real form, compact real form can have a one-dimensional torus in the center. That is exactly the Hermitian symmetry case. Therefore, for the real, if you there will be, because pi 1 of S1 is not 0, since it is Z, there will be infinitely many components, but that is the Toledo bound. This was written down 2 days ago. So, that is the interest. There are only finitely many components, and you can write down what those components are, but I do not think completely what those components are, whether it is written, I do not know. For SL2, it is in Hitchin's paper, all the components are written explicitly.
Another question? If not, let's thank.